Another type of addition reactions are the halogenation reactions, and as the name says it, we will add two halogens across the double bond. So this is the overall reaction. We have a pi bond that will be broken, and then we will end up with two halogens across the double bond. So we will get one on the right side, and one on the left side, right, of the double bond. So same thing as every other addition reactions you've seen. The double bond is nucleophilic and it will attack the X, and the other X will leave. I'm going to talk in the next slide why this happens right here, and then it will form the carbocation, and then the X that left with the negative charge will come back and attack. And we often see that with Cl, with chlorines, with bromines, and what we get is the vicinal dihalide. So it may be surprising for you how happens that I have a nonpolar molecule, or what it should be a nonpolar molecule, just as this, and the nucleophile goes and attack one of the sides. Well, as you know, these type of reactions, they can get a dipole moment, but that dipole moment is it's not always there. It's just induced because of the electron-rich double bond. So the electron-rich double bond can induce the dipole in this XX molecule, and that's how at a given time we get a delta plus and a delta minus within that non-polar molecule. Right? So halogens, because they are so large, especially chlorine and bromine, they are polarizable. And we've talked about it before, right? So these molecules are polarizable because even though they have a lot of electrons, they are quite large, and they can get that polar moment at a given time. The electron-rich, imagine it as a magnet, right? So I have the electron-rich double bond that will induce that polar moment in the molecule that it's not usually polar. So imagine it as a magnet, okay? And so the halogenation follows a slightly different mechanism from the hydrohalogenation. And the hydrohalogenation and the hydration, we go through that carbocation that forms in the middle. And here we will go through something that it's a little different. Let's look into it. For the halogenation reaction, we get a halonium ion. So we will talk about the bromonium ion, the chloronium ion. And so what it forms is that it will form this three-member ring when the alkene reacts with the X that has the delta plus. Here I have delta plus, here I have delta minus. So the delta minus X will leave, and we'll take care of that later. But for the halogen that has the delta plus, it will form this bridge halonium ion. If you follow the flow of electrons, you will see how the bond attacks here, right? The double bond will attack here, and then at the same time, these will form another bond with the double bond. And so it kind of, one molecule adds to both sides of the double bond. But then remember that one X left with a negative charge. And that three-member ring is not very stable for many reasons. You know, three-member rings have a lot of strain, and also it has a positive charge, so that's not stable. What will happen is that this X minus will come and attack one of the sides, and it will open up the three-member ring, and that's how we will get an addition across the double bond. So you see here, we compare the stability of a carbocation, that it's unstable because it doesn't fulfill the octet, so it doesn't have the octet full. And we have the bridge halonium ion, that it's not very stable because of that ring strain that I was talking about. It has a three-member ring, which is very, very tight. What is interesting about these type of reactions is that the stereochemistry that we will get. So when we form that first chloronium ion, right here, this chloronium ion, because that double bond is flat, the chloronium can come from either the top or the bottom, but both of them have to come from the same side, right? So you see here the flow of electrons, the double bond comes and attacks the chlorine, and the chlorine comes and attacks back. They both come from the same side. Either both of them come from above and we get this three-member ring pointing towards us, or both of them come from below. But in this case, they are identical because the molecule is symmetrical and you can flip it and it becomes the same one as this one. But that will not be the case for every single molecule that we're going to see out there. So remember that three-member ring forms from the same side, and that is going to be important. Why is that important? Well, because there is no way that you could get something like this with a chloronium there, with a Cl+. Sorry, actually let's draw this properly. Let me just redraw. There's no way that you can get, so if this is a wedge and this is a dash, that would never exist because the strain will be incredible. Having a Cl pointing up, a CCl bond pointing up, and then the other CCl pointing down. So that will never happen. But you can have something like this in which both of them come from the same side. And why is this important? Well, this is important because now the other Cl, the Cl minus, will come from the opposite side. So when this Cl now comes and attacks here, you see if the three-member ring is pointing down, now this Cl is going to come and attack from the top. And here, because it's pointing up, this CCl is going to attack from the bottom. So this is exactly what I was talking about. So you see here we have the chloronium ion pointing up, and it will attack from the bottom. And so this is how I will get the Cl on the top and then the Cl from the bottom. And here, because both of them are up, it's the same thing. If it attacks on this side, it will give me the Cl at the bottom here and the Cl at the top here. But these two are the exact same one because this molecule is symmetrical, right? So the backside attack will always occur when we have the Cl three-member ring pointing up. And the front side attack, in another way, if you want to call it like that, it will happen when we have the Cl pointing down, right? So the Cl minus will come from the opposite side from where the three-member ring is. So here, let's look at one example. If I have this double bond right here, it will form the bromonium ion like that, both from top or from the bottom, the Br plus from the bottom. And now the other Br that has to come and attack, in this case, will come from the top, giving me the wedge will be this compound right here. And if it comes here and it comes from the bottom right there, it will give me this compound right here. So this Br is attacking from behind, and so that's why I get the wedge. And the other one, when it opens up, it's going to open up and stay up. In here, because it's going to come from top on the right side carbon, I'm going to end up with this pointing up. And then this one, when it opens up, is going to stay where it was in the back. Now here is a little tricky because these two compounds are enantiomers. You cannot superimpose them. But in this one right here, we will end up with identical, this is a meso compound, because remember that this one right here, if you go through the exact same process that I went through here, you end up with one up and one down, and one up. But if you flip this, right, if I simply rotate this this single bond here, I end up with a meso compound, because even though it has two chiral centers right there, the molecule is symmetrical. So a molecule with chiral centers, but that it has a plane of symmetry such as this one, it will be a meso compound. So be aware of that. right? So I know that this is a new chapter, but things from previous chapters keep coming back.